Hey guys, Jeff Schultz here. Just thought I would do a quick video on how to calculate your VX and VY speeds using some really simple flight test data. I like to use the sawtooth climb descent method, and I'm going to demonstrate how to do that. I got a little bit of cockpit video that I'm going to attach, and then we'll go through the actual data numbers. So what are we trying to accomplish here? Well, if you look in your typical pilot operating handbook, you're going to see a performance section that's going to list your speeds, including your climb speeds, your best angle of climb, VX, your best rate of climb, VY, and you're going to need a way to use flight test data to accurately predict what those are. So I'm going to show you how to do that. So what we're looking at here is a section from my pilot operating handbook that I have put these charts in based on my flight test data. You're also going to have things elsewhere in the POH, let me show. So your typical airspeed limitations. These are ones that the manufacturer has in some cases specified, like your never exceed speed. In some cases you're going to determine them experimentally, like your stall speeds and your VX and VY speeds. So you're going to need this data to fill out your POH properly. And then depending on how you have your POH set up, you may have summary data like I've got here at the beginning of my performance section, which just summarizes the VX, VY, top speeds, cruise speeds, things like that. So all that data is going to generate this. So the way we're going to do this is we're going to use a spreadsheet to crunch the numbers. We're going to take a series of climbs. We're going to start at a known altitude. In this case, I'm talking about 4,000 foot pressure altitude, and we're going to climb up a block of altitude, in this case to 4,500, so a 500 foot block. This is my data table. I've already flown this and I punched this in, so I'm going to explain all this when we come back, and we'll go through the actual numbers. But just a quick orientation as to what we're going to gather in the cockpit. We're going to record our background information, so we've got the ground temperature, the aircraft weight that we're flying at, some sort of indication of what the weather conditions are like. We're going to fly this by setting our altimeter to 29.92. That's going to give us pressure altitude, and that way when we're set at 29.92, we can just read our pressure altitude directly off the altimeter. And then this spreadsheet here makes it easy for my data table, so I've already included all of my speeds that I'm going to do, so 55, 65, 75, 85. You can set this at whatever increment you want. You can do 5 mile an hour increments. I did 10 mile an hour increments just to make it go a little quicker, from 55 up through 105, and you can see that I haven't filled any data in here. Okay, so that's the data table that I'm actually going to print out and take with me in the cockpit. You'll see me hold that up and refer to it a couple of times. So let's go watch the video, and then we'll come back and we'll talk about what to do with the data we collect in flight.
Hey guys, I'm going to demonstrate how to collect some climb data. So I'm going to do a sawtooth climb descent series just to demonstrate. So I've got my data sheet here. It's got all my tests. I'm going to start at 55 miles an hour and I'll climb up at 55. I'll record how long it takes to do a block of 500 foot in altitude, and then I'll descend back down. And then when I complete that, I'll go to 60 and then 65 and 70. I'll work all my way up until I'm really not climbing anymore. I've got 130 on my sheet, but I may not even get that high. We'll see how it goes. Then we can plot all this data, and we can get a good idea of how much power is required in the sonics. So notice I've got the throttle pulled way back right now. I'm starting at my slow speeds, so I wanted to get slowed down so I didn't have to do that too much. So I'm going to be doing 55, so I'm going to transition back to a climb. So let me get the power put in here, and I'm going to pick up my 55 mile an hour climb speed, and I'm going to let it stabilize. So I'm going to start my watch at 4,000 feet pressure altitude, and I'm going to stop it when I get to 4,500, and then I'll record how long it took to climb that. So right now my task is just to get stabilized on a climb at 55 miles an hour. All right, coming up on it, and start. So I'm going to hold 55 as near as I can. And I'm at 4180, 42. There's 43. 4460, 80, and stop. That was 40 seconds. So I'll record that. Okay, let me get low down here. Outside air temp was 70 degrees. 40 seconds. So I've recorded that in my data sheet because I'm going to need that. All right, so now I climbed up a little bit past my target altitude. I'm going to do the same thing coming down. So let me get my... I'm going to get turned away from the back into the flat area here. Okay, so I'm going to bring my power off to idle. Okay, and I'm going to hold 55, and there's 4560, there's 55 on the speed, and there we go, start. And I'm just going to descend, holding my 55 mile an hour target speed until I get back to 4,000. So I did a 500 block going up and a 500 block going down. $4,200. $41. And stop. 54 seconds. Bring the power back in. So now I'm gonna set up for my next run. Again, 4,000 to 4,500. So let me get turned. And I need to go down a little bit because, again, I need to make sure I stabilize. Okay, so I'm at 3,600. 400 to 500 feet is enough to kind of get stabilized in the climb. Okay, so let me record that. $54 seconds. All right, my next one is 60. So let me get configured again. My power set. I'll start climbing at 60. So you can see it takes a while to get slowed down and get configured. So you got to leave yourself plenty of time before, otherwise you're kind of, you're doing a zoom climb. Got extra speed that you're translating into rate of climb, but it's not steady state. All right, so I'm coming up on 4,000. And start. There's 44. And stop. 32 seconds. Okay. So we got that. Let me bring my power off. And we're going to do it coming back down. Got my engine set up and leaned. Power's off. Got the mixer pulled back. Looking for my target airspeed. Once again, it takes me a little bit to get dialed in. And there we go. 6560. And start. I'm holding my target airspeed, 4250. Watching that airspeed. And stop. 47 seconds. Okay, so I'm not going to do the full series here. So 47 seconds coming down. My temperature is still holding. So I just kind of fill in my tables as I go. And then I'll take this and I'll plot it on my Excel graph, and it will give us a curve of how much rate of climb we get at each of our airspeeds. That curve will have it'll start off down here at my low airspeeds. As I get into my peak climb airspeed, it'll go up. So I get the highest amount of rate of climb. And then as I go faster than my peak climb airspeed, the rate of climb will start to drop off again until eventually I can't climb at that airspeed. So at 200 miles an hour, I can't climb at 200. So that's going to be, zero, the type of thing. We can plot that, and the shape of that curve is important because it tells us something about the performance of the airplane, the design, the drag, all that. All right, so hopefully that shows a little bit about how to do a sawtooth climb descent series. And we're just going to do this. We want to try to choose a nice day where it's not bumpy. You can see I have to really kind of watch my airspeed. I got to start and stop my timer and record my figures. So you don't want to be bouncing around in the airplane. It just makes it hard to do all that, especially to hold a consistent airspeed. And then we'll take all this back and we'll plug it in. So, all right, I hope that helps.
Okay, so the flight's over, and you saw me actually fly the test. One of the things that you really got to watch is to make sure that the airplane is fully stabilized in your test point. So if you're going to do a climb test at 65, you got to get the airplane slowed down, you got to get climb power put in, and then you got to give it sufficient time to stabilize in a climb at 65. And it shouldn't need a whole lot of movement on the stick once it's stabilized. If you're having to constantly adjust, well, you're not quite stabilized yet. I like to go anywhere from 300 to 500 feet below my starting altitude, and that way I can make sure that I bleed off any excess energy and I really get it stable. So in this case, my starting block is 4,000 foot, and I'm going to go up to 4,500. I'm going to start it at 3,500. I'm going to get my 65 climb speed and then let it really just kind of settle in, and then I'll start my stopwatch and and collect the data from 4,000 to 4,500. So I've taken all these numbers here and I've already plugged them in. So consistently, I was getting 70 degrees in the cockpit, and that's just going to help us correct for density altitude, which the spreadsheet is going to need. So you can see I've entered those 70s here. I didn't enter them on every line because it seemed a little redundant, but just to show that I did record it at each interval. And then I've got the total number of seconds for each block. So this is 40 seconds to go from 4,000 feet to 4,500 feet at a climb speed of 55 miles an hour. And then on the way down, it's the same thing. I stabilize it. I go up past 4,500, which in this case is my starting block coming down. I go past that. I get it all stabilized, descending at 55. And then I do a 500-foot block coming down, and I time that. And that was at 54 seconds, and I've entered that here. So here's all of my data that I've entered into my data sheet. Now, I've done this on the computer so I can make this video a little easier rather than looking at my handwritten notes. In the cockpit, I've got a printed out data sheet, I've got a pen, and I'm making these notes longhand, and then this can just go in your files or just toss it when you're done. This is just for demonstration video purposes that I put this back into the data sheet here. We're not actually going to use it here. So we come back after the flight's done, and we open up our climb descent performance flight test spreadsheet. I've just extracted this out of my larger spreadsheet, and I'll put a link to where you can find this simplified flight test spreadsheet if you want to go look at it yourself. So what I've done is I've translated all of the notes that I made on my data sheet. So there's my conditions that I flew this morning. Clear sky, humid, hazy smoke layer at 3,000, calm winds, and then the date, temperature at the ground, and my altimeter setting, just so I have all the data if I have to look back on this later. I've captured my aircraft weight. In this case, empty weight plus me plus 14 gallons of gas put me at 950 pounds. And again, I just want to be complete, capture all that. So I've broken up the data sheet into two segments here. So this upper section here is for the climb at wide open throttle. And then this lower section here are all my descent series. So you can see it looks a lot like the data sheet. Here's my speeds I'm doing, 55 up through 105 in 10 mile an hour increments. There's my starting altitude and my ending altitude. I'm starting at 4,000 and I'm going up to 4,500. Here is the time, and these are again right out of my data sheet. So 40 seconds. That's what we got right here. So I've entered the time, so 40 seconds, 32 seconds, 32 seconds, all the way through. And then the temperatures that I recorded, all 70 across the board here. And then same thing coming back down. So there's my 55 mile an hour descent line, starting at 45, going down to 4,000. And there's my time, 54 seconds. Now, all of this over here that's not shaded, this is all just, the spreadsheet does all the work for you. So you can see that, we've got the altitude block. So there's a 500-foot altitude block. Well, it's just doing the math for you. So it subtracted the ending and the starting altitudes, and it gives us that. It gives us our average rate of climb in feet per minute. So these numbers here, so starting at 750, 938, 968, and then back to 938. So pretty consistently, right around there. It's kind of an oddity on this particular trial. The rate of climb didn't vary that much, which is a little unusual. And then it calculates density altitude. So that makes it nice. So you need density altitude to be able to get true airspeed. And then you need true airspeed to be able to calculate flight path angle. Flight path angle is going to be useful for other things, not so much in here, but we're going to use it for calculating our takeoff over 50-foot obstacle and our descent, landing a distance over a 50-foot obstacle, because the plane flies along a flight path through the air, and this is what's going to tell us what that flight path angle actually is. So we'll come back and we'll extract some numbers off of this later in our flight testing. And so it does the math for you. So we've got all of our flight path angles right here, and then our negative flight path angles for our descent coming down here. All right, so very simply, all we had to do was, once we got all this configured, we really just plug in our times in seconds, and then the spreadsheet spits out everything else. So scrolling down in here, we've taken the data and created a couple of graphs here. So this first one is graphing the flight path angle in degrees with our observed airspeed. So, at our 55, there's our 55 climb, and there's our 55 descent. Likewise, there's our 85 descent and our 85 climb. So the Excel has just created these curves matching the data that we're seeing. And what we're going to do here is we're going to visually extract some numbers off of these curves here. And so what I've got down here is I've got a series of cells that help you just sort of extract those numbers. So just going line by line. So the best angle of climb, Vx, is at the peak of the full power climb curve. So I'm reading this cell right here. So here's the climb curve right here, and we just look for the peak or the highest number. These are lower, lower, lower. This is kind of getting higher, and then it starts to drop back off again. So right around in here, right about in there, is our peak. So that's 60 miles an hour, that's 70, that's 80. So we're somewhere between 60 and that's the 65. So somewhere just a little bit below 65. So we'll call it maybe 63, 64. So that's the peak. And so I put in 64. And this is just for me for record keeping at this point. So I've extracted that 64 as the peak off of this graph. Okay, and then I look at best glide. Best glide is the peak of the engine idle descent curve. So here's engine idle. This is the descent curve. And we're the same thing. Lower, getting a little higher, and we kind of flatten out, and then we start to drop back off again lower. So somewhere around in here is where this curve has its maximum value. So the peak is somewhere right around 80. And so I've entered 80 on this cell right here. Okay. And then this last one, flight path angle. This is the power off glide speed of 80. What is our descent angle? And that's going to be important for when we're descending for landing, coming in over the trees at that 50-foot obstacle. We need to know what our flight path angle is so we can plug that in and get our landing distance. So what we're going to do is, I've got this note here that talks about it. It says, using the speed we just determined, so the 80 miles an hour, go back and look at the data that we plugged in, and then we're going to just find the flight path angle that corresponds with that number. So we're looking for 80 in our data table, so we go back up here to our descent data. This is all of our descent data right over here, and we're looking for 80. Well, I don't actually have an 80 entry here. I have a 75 and I have an 85. So there's the angle for 75, negative 5.39, and there's the angle for 85, negative 5.36. So I'll just basically take the middle, which would be about where 80 would be, and I'll call it minus 5.3738, something like that. So minus 5.37, and I've entered that here. Okay, so that's the first graph that we do. So we extract some numbers off of there for the first graph. The second graph, you've probably seen numbers like this before. So we plot our rate of climb in feet per minute on the vertical axis and our speeds on the horizontal axis. And this is the curve that we get right here. So there's 55. At 55, we were doing about 750 feet per minute. At 65, we were up to, 925, something like that, and all the way through. So 75, 85, 95, all the way through. So we get this curve. Now notice that the Excel has fit an approximate curve between all of our data points. And there's this one that's a little higher. It's kind of an anomaly in the data. So if we were to refly this, we might see that, that was just kind of a weird thing. Maybe we weren't fully stabilized. We had a little extra energy going into the starting block that hadn't quite, been dissipated. And so we got an artificially high rate of climb because we had that little bit of excess energy. Bottom line, we might want to go back and refly that just to be able to see that, yep, that really was, quite a not stabilized data point. But the nice thing is Excel kind of sets this curve in here for us, so we don't have to necessarily have a perfect fit to be able to extract some useful information. All right, so if you remember back to ground school, when you determine the Vx and Vy, your Vy is your maximum altitude gained per unit time. So we can pull Vy directly off of the graph. It's the max rate of climb, that we're going to see. So We want to go up as fast as possible, so we're just looking for the very topmost point on this curve. So this is low, this starts to drop back off. It's somewhere around here. This is about where the top of the curve is. So right about there, that's right about our 85 mile an hour data point. So I picked off VY as that 85, and I've entered it in that cell right there. All right, this next part is a little bit tricky. So we talk about Vx being the line that's tangent to the curve. So if we take this line starting at 0, 0, and it kind of just comes over and it just lays down against this curve, where this purple line touches our dark blue curve, that's the tangent point. And so what I've got here is I've drawn that line rather than having to do it with a pencil and a ruler. And I've got this note here about guessing and checking. So I can just try values. So let's try 1,000. So I punch in 1,000, and it's going to set a tangent point. Well, that's not right, because that's not tangent to the curve. So it's not 1,000. Let's do 500. Now it's getting worse. I'm going the wrong direction. So I need to go the other direction. So let's try. I tried 1,000. Let's try 1,500. 1,500 is we're getting closer, but now we're a little too far the other way. So it's somewhere between 1,500 and 1,000. So let's just do right in the middle, 1,250. And now that curve pretty well lays down right on top of it. It's not quite. It's kind of overlapping. So let's try 1,270. 1,300. There we go. So now we have a nice tangent. That purple line is tangent right there. Just touching the curve, and I can pull a number off of there. And at that tangent point, it is somewhere around 55 to maybe 58. So there's our Vx point right there. Okay, so we picked these numbers off of our data curves, and then our last one is talking about our glide performance. So if you are familiar with glide polars, it basically just shows how fast are we coming down at each of our airspeeds. If we are at our slowest airspeed, we're coming down the slowest. So at the top of this curve, whatever the highest point is, that's our slowest rate of descent. And as we move along this curve, we get faster and faster rates of descent. And that kind of makes sense. If we want to do 120 miles an hour with the engine not making any power at idle, we're going to have to point the nose down, and we're going to have to trade altitude to get airspeed. If we wanted to do 200 miles an hour with the engine at idle, we'd have to really point the nose down and go really, really fast. And so we'd have an even higher rate of descent to sustain that 200 mile an hour. So what we're looking for is, ideally, we want to fly enough value so that we see a peak and then it drops back off. So if I was to refly this, I'd want to try to get some data in the 35, 40, 45 mile an hour range, because I would expect this to start dropping off. And at our stall speed, our rate of descent goes up a lot. So we might have 1,000 feet a minute, at a stall speed of 40 miles an hour. And so we have this very sharp drop right here. Now, this is kind of hard to get this data because you've got to fly power off really close to the stall, and you got to do that very precisely on your airspeed, and you got to manage your stopwatch to get the time, all that. So this data is a little hard to get, but ideally that's what we would want to do is to see this curve start to fall back over. We can make some good values here. We can make an estimate about these. So as before, I'm gonna guess and check and set my tangent line. I've already done that. It's minus 970. It's exactly the same thing. Try minus 1,000 and see if that's close. Try minus 1,200 and see if that's closer or worse. And then you just sort of zero in until you get this nice tangent line. And tangent meaning it's just touching right there. So at the point where it just touches the blue curve, that is about right there. Right about there. Just a little bit below 80. There's our 80. There's 75. So we'll call it about 78. And that's what I've done there. The tangent point of about 78. And then the slowest descent is the peak. So whatever this highest value is, well, that's 55 because I didn't go any slower than 55. And so I'm grabbing it right off of there. 55 is the slowest descent. And so I've got all of my numbers there. So now I've just created this summary chart here that just grabs all these different values and just sort of puts them in. We can cross-check. So we've got an estimate of Vx on 1 at 64, and we've got another estimate of Vx at 58, and so we're just averaging these two out. And so our Vx is somewhere in the neighborhood of 60, 61, and our Vy, same thing. We've got a Vy picked off of our chart up here of around 85, and so that's summarized here. Our best glide speed is what we determined over here with the 78. Best glide is that tangent point there. And so now we've got our best glide speed determined. Our slowest descent speed is on the glide, which is, we want to come down as slowly as possible. So that's our speed of 55. And then we do the math and we calculate our glide ratio just so we have some idea of how efficiently the airplane glides. And we're showing a 10.6 to 1 glide ratio. So, it's no sailplane, but, it's a typical light GA airplane type of glide ratio, 10 to 1. All right, so now we've got all the data that we can use to fill out our pilot operating handbook. So we can go back in here and we can start filling in these numbers. And we can go and do our charts. So these are other performance charts, but we can generate nice, clean rates of climbs and glide performance polar charts and all that we can insert into our pilot operating handbook. And in fact, what I've done here is I've taken this chart and I've just cleaned it up. I've taken off the individual data points and just left the curve. And so now once you get a series that you're happy with, you think, yep, that was a good test day. I collected very accurate test data. I'm happy with all that. Now you have this glide polar that you can drop in your pilot operating handbook, and it gives you useful information. So in this case, I can see, at any speed at 80 miles an hour, I would expect, come down to the blue curve, I would expect to see a minus, we'll call it 750 feet per minute descent. And at 55, I would expect to see somewhere around 550 feet per minute. And so that's a good, useful chart that we can put into our POH. And this was a cleaned up version that makes it easy. So if you see this and you think, well, this data doesn't look great, maybe I need to work on my flight test technique, that's fine. Just go back and redo it and re-enter your new data up in here, and it will just recalculate everything. And you can actually just add additional data. You could have data from different days overlaid on top each other if you wanted to try to get some sense. But anyway, so you can get a good test set that you like, have it do all the math for you, and it spits all this out. And so you can see how easy this is. Once you have the data, you literally just sort of plug it into your times, let it do all there, and then you just have to read and interpret the charts, make your summary observations in these cells, and it will give you your summary table right here. And that's all you really care about. So now in one 30-minute flight and 30 minutes of data analysis using the spreadsheet, I've got everything I need to be able to fill out my performance section and for Vx and Vy. And then I've got my glide performance. And more importantly, I'm ready to go do the next test, which is going to generate this chart here, the rate of climb at Vx. The rate of climb at Vy. And so we're going to need to know what our Vy speed is before we can go climb this. Well, now we've done that. We've got a target Vy of 85 miles an hour, and we can go climb from a very low altitude to a very high altitude and see how our rate of climb starts off high and then gradually tapers off until it eventually is just not useful anymore, and that's our surface ceiling. So again, really powerful tools. The spreadsheet makes it easy, and you can go find the link in the description for a link on a simplified flight testing spreadsheet that you can use on your own projects. Hope this helps. Go out there, gather some test data, and use it to really enhance your POH. Okay, thanks. Fly well.